All right, so welcome back. It's week 2. We're going to continue with our discussion of brute force algorithms. On Friday, we went through an entire demonstration of how to generate combinations. So today we're going to look at how to generate their, cousin or whatever, permutations. Given a set, again, the same setup as before, where we're only going to concern ourselves with permuting a bunch of integers. Because if you can permute integers 1 through n, then you can always map that back to whatever you're actually trying to permute. If you're trying to arrange like 5 people in a row for a picture or something like that, how many ways are there of doing that? Well, just assign them numbers 1, 2, 3, 4, 5, and then just arrange those numbers, map them back to the people that were assigned those numbers, and you've got a permutation of people rather than numbers. Before we continue with this, though, I wanted to make sure that we're all on the same page. And give a little bit of a review of what permutations are. So a permutation is an arrangement. And that's the key word right there. Order matters. Right? Oops. I don't know why it's not updating here. There we go. I just had to focus on it for a little bit. A permutation is an arrangement of elements. Right? So, for example, oh, come on, really? All right, wow, that is an extreme delay there. Of elements, okay? Hopefully that gets better as we go along here, but anyway. So let me go ahead and go back to the notes here and just write it down instead. So it's an ordered arrangement of elements, right? Unordered arrangement of elements. So if I have n elements to begin with, how many ways are there of permuting those things? So let's just take 3 people, right? A, B, and C, right? Alice, Bob, and Carlos. I can put them as A, B, C, right? In fact, now I will go back over here as an example. Come on. Focus on this. So if I've got A, B, and C, what's another arrangement? I could start with A, but instead of going B, C, I could go C, B. I could start with B instead, and then go A, C, or B, C, A. There we go. Or I could start with C, right, and then go A, B, or B, A. And I've enumerated them all here. Okay. So how many were there? If n were here were 3, then the number of permutations is 6. N factorial in general. It's going to be n factorial. Now you can talk about generalized permutations where, and we will eventually talk about it a little bit, but you can talk about generalized permutations where you've got 50 people. You want to select only 5 of them and then arrange them in a row, right? That would be 50 permute 5. We're always going to be looking at n permute n, right? At least for now, okay? So in general, there are n factorial possible permutations of n elements. There we go. So what I want to do is I want to develop an algorithm here, so, similar to what we did before, to generate all possible permutations. And the algorithm that we're going to develop is going to work piecemeal. So given the current permutation, I just want to go ahead and generate the next permutation. And then you can go into this big loop to do it over and over and over again until you've done all the possible permutations. It's also going to work very, very similar to the combinations that we saw on Friday, where you're basically counting, right? So for example, let me come over here. Wow, okay. And if I have, like, say, 1, 2, 3, 4, 5, 6. In other words, n is equal to 6. What's the next permutation if you were to look at this from a counting perspective? Now remember, you can't repeat elements. You can't have 6, 6 or 5, 5 or something like that. So the lexicographic next one would be what? Yeah, go ahead.
1, 2, 3, 6, 5.
1, 2, 3,
4, 6, 5.
4, 6, 5. There we go. All right. What would the next one be after that? 1, 2. Well, 6 has appeared here, right? Now 6 is over here. What's yeah, 6, 5. Then what's next? 2, 3, 5. Okay. And then what two things I have left over are 4, 6, right? So lexicographic order here means if I were to take all the possible permutations, shove them all together, and then treat them as numbers, and then I sorted those numbers, that would be the order of permutations that I want. Okay? How do we go about doing that? Well, again, it's the same idea as before, that you've got some sort of permutation, and then you've got this element here that needs to be incremented. It goes to the next one. And then over here, this will be incremented or next, right? And then over here, what we need to do is we need to start over, just like when we count, right? If I've got 99999 and I add one more, I carry everything over and change this guy over here, and then I start over on everything else, 0, 0, 0, 0, 0, right? The one that we looked at on Friday basically did that, but instead of starting at 0, 0, 0, 0, because you can't repeat things, it went to the next combination among those things. So over here, we're going to do something similar. We're going to start over by sorting these elements, right, once it appears. Okay? So this suggests a step-by-step process that we can perform here. Oops. Sorry. There we go. All right. So given a current permutation, and I will label it just as before, A1, A2, ... AN, we want to find the next permutation. And to do that, the first step is to find that element that needs to be incremented to the next element. So what we're going to do is we're going to find the rightmost, that is the last, pair of elements, a sub I and a sub I plus 1, such that a sub I is strictly less than a sub I plus 1. Right? So we're going to find these two, we're going to start at one end, at the right end, and we're going to work our way back to the beginning until we found this pair that is, that's in order, basically. Okay? Then what we're going to do is we're going to find the smallest element to the right of a sub I, right? The tail of the permutation is what we call this, larger than a sub I. Right? Then we perform two operations. First of all, we swap let me give this a name. Call it A prime. Right? There we go. Swap A prime and a sub I, and then we'll we'll order the elements to the right of A prime. And when I say right of A prime, we're going to take A prime, we're going to find A sub I, and we're going to find A prime here, and then we're going to ultimately swap them, and then we're going to sort everything. Now, after that swap operation, that's when we do all this sorting over here. Okay? So let's take a look at an example here. Hopefully it is speeding up, maybe not. I'll go with this example. So let n be 6, and magic, we've jumped. In general, if I've got 6 here, how many possible permutations are there? 6 factorial, which is, off the top of your head, 720, right? Yeah, all right, well, 6 times 5 times 4 times 3 times 2 times 1, 720. I'm not going to start, at the very beginning when nothing interesting happens. I'm going to jump into the middle of this stuff, and suppose that we have the current permutation as 1, 6, 3, 5, 4, 2. Okay? And again, apologies for this this lag here. Okay? So we want to find the next possible permutation. Now, again, remember that we are searching for the rightmost, that is the last pair, that is in order. Okay? So what about 4, 2? Is that in order? Nope, so not that one. What about 5, 4? Is that in order? Nope, not that one. 3, 5, is that in order? Yep, excellent. So we found our candidate pair right here. This is A sub I, and this is A sub I plus 1. A sub I plus 1 is no longer relevant. This is the thing that we want to focus on now, the 3. So step 2, or so 1, find last pair that is in order, right? And of course, and by the way, algorithmically, if you're going to do this, you can start at the beginning, but why would you? Right? Okay, this pair is in order. Oh, I found another rightmost pair that's in order. Oh, I found another rightmost pair that's in order, right? Instead of continually updating that, just work from the right and work your way down. 2, we are going to find find A prime, the smallest element larger than A sub I to the right. Okay? And there I'm just rewriting what I already put into the notes here. So in other words, I'm going to be looking at 5, 4, and 2. Which ones, first of all, what about 2? 2 is the smallest one, right? But it's not larger than A sub I, which is 3. So 2 is not a candidate here. 5 and 4 are both larger than 3. So they are candidates. Which one do I want? I want the smallest one. So that's going to end up being my A prime. Okay? So now my final two, my operations here. A, swap A prime, or A sub I and A prime. And so I'll do this in steps here. This will end up being 1, 6, 4, 5, 3, 2. Right? And then B, order, that is sort everything to the right of A prime. Okay? It's really throttling me today. Well, let's just make sure that everything's fine online. Yep, sounds like it. Okay, so sort everything to the right of A prime. Now remember, A prime is switched positions, right? A prime is over here. So what I end up doing is I end up sorting all of these elements over here. And I'm left with 1, 6, 4, 2, 3, and 5 as my next permutation. And that's it. Okay? Do we want to go one more iteration? All right, so 1, 6, 4, 2, 3, 5. 1, 6, 4, 2, 3, 5. Again, step 1, find the rightmost pair. Rightmost in order pair. Maybe this isn't going to be that all that interesting though, right? Why? What's my rightmost pair? That's in order? 3, 5. Right? So what am I going to end up doing? I'm going to end up swapping them, right? Giving me 1, 6, 4, 2, 5, 3. And then I'm going to end up ordering or sorting everything to the right of 5, but there's only one thing there. And so it's not all that interesting. When do I stop, by the way? So you said we observed that the first one was 1, 2, 3, 4, 5, 6. And then the next one was 1, 2, 3, 4, 6, 5, ... After 720 iterations, what's the last one with the lexigraphically last permutation? Sorted in reverse order, exactly. 6, 5, 4, 3, 2, 1. Right? And what condition can we use or to develop to say that we're done. There's no other there's no other permutation here. Yeah.
When it's equal to n factorial.
Oh, okay, we could keep a counter, definitely, right? But just by looking at this, what can you say? Find the rightmost pair that is that's in order. Is that it? Nope. Is that it? That it? That it? That it? Nope. Is there a rightmost pair that's in order? No. At which point we can stop. Yeah.
Is there a more efficient way to check that?
Well, let's talk about efficiency.
You set from the end, then this will be.
No, you generally want to start at the end. But in general, again, there are n factorial permutations. So, if you're resigned yourself to generate all possible permutations as a problem to begin with, then this is going to be obviously order n factorial, which is super exponential. You can show that this is big O of n to the n, right? Using Stirling's approximation formula. It's a continuous formula version of the factorial function. The factorial function is also called the gamma function, right? The gamma function, unfortunately, is discrete, right? It's only defined for integers. 0 factorial, which is, by the way, 0 factorial is what? 1, right? Just because it works, right? How many ways are there of arranging nothing? Nothing. Or there's one way of doing that. You do nothing. 1 factorial, 2 factorial, 3 factorial, 5 factorial, 3.5 factorial? Does that make any sense? No, but sometimes you want it to make sense because you want to take this factorial function and you want to, say, integrate it. Or can you integrate discrete functions? No, because you're just adding up a bunch of lines which have no area. Can you take the first derivative of discrete functions? No, because it's not defined. You have to define a function from above and below, and for its derivative to exist. And so the Stirling's approximation formula gives you a formula that works for all of those values, but that is continuous, so you can integrate it. Right? We won't get into that because it's not part of our focus here. Right? So given that, let's go ahead and develop this algorithm here. All right. Let's see. Actually, I can go over here and let me go ahead and add. This is just from the book, or from my note set, I should say. Refrain from calling it a book. There we go. So there is the next lexicographic permutation. And it codifies exactly what we just described. You start at the end, and you try to find a pair, the lastmost pair that is in order. So while they're out of order, you just simply continue to move left. Once you've found that thing, A prime, that's the thing that you want to then swap. Note here that I put A plus 1, simply because I go one extra. I only break out of that while loop after I've gone past that pair. And so I want to correct for it by going back 1. And then I need to find the element to the right of that element that is the least element that is greater than it. So if it's greater than what than a sub I, and it is less than what I've found so far, then I update A prime here. Right? And then I swap those two. Or sorry, I start A prime. That's not what I'm doing on line 4. I start A prime at the next element. Right? And then I swap them, and then I sort them. Okay? So let's try it out in Python here. Def next perm, right? Current, and do I need n in this case? If I have a permutation of n elements as a list, you've already got it, right? You've already got n. So again, I do want to mention something here. So after class on Friday, somebody asked, do we need to write documentation? And it's always a good idea, and I'm glad that they asked that question, because it allowed me to come up with a teachable moment, and it allowed me to really come to the realization that there's definitely a difference between in-person and what we all experienced last year. Because as I was writing this next combo on Friday, right, I started just writing code, and I immediately saw from a couple faces out in the audience, like, wait, what are we doing here? And so I said, okay, well, I backed up. And what did I do? I wrote documentation. I wrote documentation and I gave an example here, right? So that's the value, that's the worth of writing documentation. You write the documentation before you start coding, and you know exactly where you're going to go. I knew personally exactly where I was going to go because I've written it before. I don't come into these things and start ad-libbing it. But I realized that documentation is not just for me, right? And I didn't realize this, but this is something I try to impart on everybody. Documentation is not just for you when you're developing the code. It's also for others to tell you exactly what the code is supposed to do, right? So yes, you should get into the habit of writing documentation first. I'm not going to grade on it in this class, but you should do it, right? And this is, does anybody remember the JEP for this formatting here? Where you use multi-line, so 3 quotes here, multi-line, and in a departure from what we're used to, like say doc-style comments that go above the function, they go inside the function because it's Python. I don't know. Anyway, given a current permutation of elements 0 through n minus 1, generates the next lexicographically next. Next permutation. Returns, generates and returns, I should say. Returns none if no further permutation, if there is no next permutation. Okay. So for example, and then you can come up with another example here, 1, 2, 3, 4. The next one would be 1, 2, 4, 3, etc. Okay, so how do I go about doing this? Well, first of all, I'm going to take a cue from what we did last time, and I'm going to design it such that you give me your permutation. I'm not going to muck with it. I'm going to create a new permutation and give that back to you so that you have the old permutation and the new permutation. So that means we're going to use that deep copy function again. Right. Result is equal to copy of the current. And now we're going to manipulate the result and ultimately return the result. Don't forget that. Right. I got myself into trouble last time by not forgetting that at the end, I think, maybe. Okay. Well, first of all, I'm going to start at the last element. Actually, we're starting not at n. We're starting at the second to last element here, n minus 1. Why? Because I'm going to be comparing a sub I and a sub I plus 1. If I start at the end, then I'm comparing something that's off the list. So I will start my I here at n, length of the current minus 2. And remember, we are adjusting here for 0 indexing. We're going to be 0 through n minus 1. We're not, in the pseudocode over here, we were assuming 1 through n. Okay? And that's why I'm immediately subtracting off 2 here. So while they're out of order, decrement I. Right? So while result sub I and versus result sub I plus 1, I will decrement I minus equals 1. Now, versus, of course, that's not right. Right? What do I want? Strictly greater? I could go strictly greater than or equal to, but do I need to use equal? These are all distinct elements, right? You'll never have equality. Yeah?
In our assignments, if we have to account for like bad input, would we have to create like a separate thing for like if two numbers are equal?
As far, I mean, not real. I mean, that won't come up with this, but you do have to account for bad input when you parse things. So Remember that you're not only being, your programs are being tested against all the official test cases, which you have to pass, but your programs are also being tested against randomized peer test cases. So, Alice turns in 2 bad test cases, and then Bob tests his program against them, and they fail, right? Well, it's on Alice, it's not on Bob. But Bob can be good about it and say, defensively program and say, okay, well, that test case is bad because this number is not of the format required, and so I'll go ahead and email Alice and tell her you need to fix your program there, right? But ultimately, you're not going to lose points on that. But you can be a good, peer and tell them your test case sucks, right? All right, so we're going down now. At that point, we need to find the element to the right that is larger than a sub I, but that is also the least element, right? And so that will be, I'll start over here, sorry. J is equal to I plus 1, right? I'm just, and for k, in the range of I plus 2 up to n. Remember that that's inclusive, exclusive. So we're starting at I plus 2, inclusive, and we're going all the way down to n minus 1, right? Why am I going I plus 2 here? Because I'm assuming that the jth element is the element I'm looking for until I find some other element that is less than a sub j, that is also greater than it, okay? So let's see, if the result sub k is less than what I've found so far, result sub j, and, right, that's not how you do Python. It's kind of how you do Python, but it needs to be case sensitive. You can't do this in Python. I mean, you can. I think that that's reserved, but I think that's 2 bitwise operators, isn't it not? Python people? All right. Anyway, this is the Pythonic way of doing it, and I believe the only correct way to do it. And the result sub k is greater than result sub I. Remember, it has to be greater than a sub I, and then you're finding the minimum. So if this is not satisfied, that's not a candidate. Otherwise, it's a candidate, and it's smaller than what you found so far. So J will be updated to K. Okay? Now, the 2 operations. Swap a sub I and a prime. So I can come up with a temporary variable here. T is equal to results of I. Results of I is equal to results of j, and results of j is equal to that temporary variable. Right? Pythoners, tell me, is there a better way of doing this? You can use a comma, strangely enough, and assign 2 values at the same time. You can actually do this with like 3 or 4 or 5 values, however many values you want at the same time. Take the 2 things on the left-hand side and put them into the 2 variables on the right-hand side, right? And because I and j are swapped, those values in the list are effectively swapped. Now I want to sort everything to the right of j. J. All right, so Python has a sort method. What is it called? So, if a member of a method called sort, so if I went like result dot sort, I think that would work, but I want to do it a little bit differently. What's the functions? The standalone function? Sort. It's not a verb, unfortunately. Oh, I guess it is a verb. Sorted. Right? Sort is a verb. Okay, so it's an adjective or it's an intransitive verb. Do we remember our grammar? But anyway, sorted. It is in the state of being sorted, right? And so I want to sort result, right? But is that going to work? Do I want to sort everything? That'll sort the entire thing, exactly. I only want to sort a subset of it, a sub-list of it. So j up to n, right? Or, more formally, just go all the way to the end. I don't care about n. Right? Did I ever set n anyway? No, I didn't. So I'm going to leave it like that. Right? Just sort all the way to the end. Now, unfortunately, I believe that returns a new list that is sorted. So it's not changing my list. Because actually in a sense it is. But what the act of using this syntax right here is creating a new sublist. And then handing it off to the sorted method. It takes care of that, but my original is completely is still the same. So what I have to do is I have to take this sublist that's merged, and then I have to come in and replace that other sublist with it. Fortunately, there's some really nice syntax to do this. If you want to replace an entire sublist, you can. Result sub j all the way to the end is equal to sorted. Right? Same idea. Right? It looks like nice syntax, and I would argue that, yeah, that's really convenient if you're trying to do something like that. But that kind of syntax, unless you know the idiosyncrasies of the language, you'd be like, what the hell's going on there? Right? So it's nice, but what would be nicer would be a function that says, sort a part of the list, and then you explicitly give everything off to that function, and it takes care of it for you. Right? Yeah?
Is this why a lot of people tend to like Python and then some people like prefer other languages?
Yeah, myself included, yeah. Pythoners like doing things the Pythonic way because it's short, it's sweet, but at the same time it's quick and dirty. Because and then you can get list comprehensions are another thing that they really love. And if you're doing something simple, one level deep, I'd say, yeah, the list comprehensions are great. But for the vast majority of things, when you try to do something even a little bit more complicated, then your Python code becomes even more complicated than even just separating them out into other functions. Right. All right. Well, we need to test this, but before we do, yeah, go ahead.
In range n, you didn't define n, so does it
Did I use n?
for k in range?
Oh, you're right. Okay, so I will go ahead. All right, fine. I'll define n. In fact, I'll do it up here so that I don't have to use length twice. There we go. And then just to be nice about it, I'll say go all the way down to and including n. Right? I think that'll work, but let's find out if this shorthand works. Okay, so there's the combination from last time, and I'm just going to go ahead and change this to perm and n. Right. Again, what this will do is this will create a list of elements 0 through n minus 1. That's the first permutation. Then I'll also keep a counter here, and while the perm is not none, then I'll increment my counter, I'll print out permutation, right, and then I will get the next perm. Right, and I don't need n there. Right, and then print out count in the end. I can almost guarantee you that this is not going to work. Python 3, what was it, demo? Yep, it's just going to keep going. It's thrashing back and forth on those other two. Why? What's my condition here? Well, it's not none. Did we take care of that up here? Sorry, there we go. Next permutation. Right, where should we take care of that? If there is no rightmost pair that is in order, in other words, they're all out of order, 5, 6, 7, 5, 4, 3, 2, 1, 0, right? That's the last one we want. We want to stop right there. We don't want to keep going and thrashing back and forth on this. So if there is no pair, in other words, if I is less than n, or 0, then no more permutations, return none. Now, why did I put it right there? Because again, what is I doing? I is trying to find that those last two. If it falls off the face of the list, then that means that I has gone down to less than 0. Okay. Now let's see if it works. Yay. It only goes down to 5, 4, 3, 2, 1, 0. You know what? I never reset my counter. No, counts 0. 89. I'm not sure where that's coming from. Count plus equals 1. So this should be 720, right? Because 6. We got them all, right? I assume we got them all. That looks like 0. Oh, you know what? There's a lot more that begins with 1.
Yeah.
So yeah, we've got a bug here somewhere. So let's walk through this together. There's one that I know that works. So I minus 1 perm n I minus 2 minus 1 less than none I plus 1 k j, and I think that's wrong. K is great. No, that's right. J is equal to k. We swapped them j and I and j. That looks good to me too on line 23. And then I guess we'll go ahead and restore this. This is the one thing that was different. So I don't know why that would make a difference, but go ahead, whatever. Let's find out. Nope, there's still something wrong here.
Is it probably the same reason why it kept switching from 0 to 1 to 0?
No, I mean that was taken care of by this exit condition right here. Right?
If you scroll up to the first occurrence where it starts with 1.
Oh, okay. 1, 5, 4, 3, 2, 0. That looks good, but then we immediately get out of that. We're off by 1 here somewhere. And minus 2. Maybe my code doesn't work. I'm pretty sure it worked. This works, right? This is equivalent to I is equal to I minus 1, right? Pythoners? There's not some quirk in Python that I'm not aware of. For k in range, k is less than result, and results of k is greater than the result. We swap them. I, j, j, I. Right? Yep. And then result is j to 0, n is equal to result of. Okay. I'm going to give up at this point and come back at some point and find out what the hell is going on here. Perm, count. Yeah, I'm not seeing what's wrong here. Oh well. I will fix my error, whatever it might be, when I get back to my office, and I will post. I'll post what it was on Piazza. Right. But otherwise, with 12 minutes left here, let's get into some actual problems. What we've actually been doing this entire time is just generating these generic combinatorial objects, right? What I want to do now is I want to introduce 2 problems that we can immediately throw these solutions at and get a quick and dirty answer. Right? So first of all, they're both going to be graph problems. So again, remind me or let me know if any of this terminology is unfamiliar, because again, if you didn't get it from say 235, then I'll have to define it a little bit more rigorously. So let's start talking about problems. So the first problem is going to be the let's go with the Hamiltonian path problem. So given an undirected, you can go ahead and do this with a directed graph too if you really want to. But an undirected graph, G equals V comma E. And just to make sure, what's that tuple? V are? Oh, vertices. And E is what connects vertices? Edges, right? Given an undirected graph, G equals V comma E. So with vertices V, maybe we're not familiar with the conventions v1, v2, dot, 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 vn. So generally, there are going to be n vertices, and then there can be any number of edges up to n choose 2, because how do you form an edge in an undirected graph? You have to choose 2 vertices, and you draw a line between them. So n choose 2, that would be, if all of them are there, that's called a complete graph. But here are the end edges, E, right? That could be some subset. It could be an empty graph. It could be that you have just a bunch of vertices and none of them are connected, in which case there are 0 edges. But there could be as many as n choose 2 vertices, or edges, excuse me, yeah.
So is the graph just like a set of vertices on
It's a,
existing, coexisting?
come on, there we go. So here's the example I would go to if we had more time. There's a graph. What are the vertices? A, B, C, D, E, F, and there are 6 of them. What are the edges? They are connecting A and B. They connect B and D. Is there an edge from D to E? Nope. So that's one possible graph with those 6 vertices. Okay. So given that directed graph, determine if there is a Hamiltonian path or not. Now remember that we already described a few types of different problems. There's optimization problems where you know that there's a solution, you just need to find the optimal solution. There are decision versions where you don't know if a solution exists or not. We don't know whether or not a Hamiltonian path exists in any particular graph. There also could be functional problems where, all right, suppose there is a Hamiltonian path. I also want you to tell me what it is, rather than just telling me yes or no, there is one or there is not one. Right? So what is a Hamiltonian path? A Hamiltonian path is a path in a graph that visits every, or traverses is the better word, traverses every vertex exactly once. Right? So you can have non-simple paths where you go back and forth between an edge, or you traverse an edge more than once. We're not talking about those. You can have a path in the graph that visits 1, 2, 3, 4 vertices. That path is of length 3. Right? What I want is a path. Does there exist a path that traverses everything? Right? So is there a Hamiltonian path over here?
Yeah.
All right, tell me what.
A, D, B, E, C.
A, D, B, C. Oops. All right. Undo this. I don't want that. A, D, B, C, E, F is what you said?
Yes.
Okay. Is there another one? What?
A, B, B, C, A, B, B, E, F, C.
F, C. Or go to C and then F, right? So there are several here, right? We only are concerned with finding at least one. Does at least one exist? Not only that, but we're not concerned with outputting this path. We're just concerned with a yes or no answer. Kind of like writing a Boolean function to do this in Python. It returns true or false. Versus like what we've just written, it's kind of a functional function, for a functional method, that returns a list. Something else that would might return an optimal list or something like that. Okay? So that's a Hamiltonian path. With our final few minutes here, let's think about one possible solution. Right? One possible brute force solution. Ideas? And I'll hint here, combinatorial solution. What have we looked at so far that we can just throw at this problem immediately? Yeah?
Generate every combination and check if that is a valid path.
Generate every combination of what?
Of every single vector. No.
Every vertex? And check if it is a Hamiltonian path. I left that blank there. What do I want to generate again?
Every combination?
So combinations, or does order matter or not there?
Yeah. Wait. Permutation.
Okay, permutations. permutations. There we go. Every single permutation of every vertex, and then verify. Why? Well, remember, what did you tell me was the blue? A, D, B, E, F, C. What was the red? A, D, B, C, E, F. Okay. And there are a couple more you can go. But is this the same thing as, say, I don't know, A, B, C, E, F, D, right? If order didn't matter, this thing and this thing right here would be the same. But does that form a path? A, B, C? Nope. There's no path, there's no edge here over to that one. So order matters, because some of those edges might not be there at all, right? Okay, well that suggests some really quick pseudocode. What? Yeah, we've got 4 minutes here. So, has, let's see, for each permutation of V1 through Vn, right? And I'll give that permutation a name, pi. Usually we denote permutations with pi. Don't ask me why, we just do. Yeah, go ahead.
Are the edges just defined as sets of pairs of vertices?
Sets of pairs of vertices. And those pairs are unordered because for an undirected graph, because AB is the same thing as BA. If it were a directed graph, AB arrow is not the same thing as BA arrow. And so you'd have a different definition for directed graphs. We're only dealing with undirected graphs so far, okay? Magic of pseudocode, right? We already did that. In fact, we did it in Python, right? So for every permutation of vertices, verify. So verify pi is a path. Right? So that's simply going to be for I running from 1 up to n minus 1 if v sub I and v sub I plus 1 is not an edge, then that means that, well, like our example, we can't go from D to E or whatever it was. And so we immediately say, nope, that's not it, right? So I need a flag value here. Is valid will end up being false. And you can break out of that if you want to, right? Otherwise, and so I do need to set that up here, is valid. We'll start out with true. And if we ever find something that says it's not true because that edge does not exist there, then we can say, no, that's not going to be it. Right? So if after I get done verifying that it is a path and it is valid, then output, yes, it does indeed have a Hamiltonian path. Otherwise, if I get through every single possible permutation and I don't find anything that works, what can I do? Output, no. There is no possible and no permutation of vertices gives me a valid path that visits every vertex exactly once. And because we're permuting them all, we're not missing anybody. But because we are using this in our outer pseudocode here, what is the complexity of this going to be? Just think of my elementary operation as being everything in here. That's 1. How many times do I execute that entire code block right there? How many permutations are there? N factorial. All right. Is that going to work for graphs even of, let's say, 20 vertices, 30 vertices, 100 vertices? No, that's way too big already. All right? But your assignment 2 has graphs that big. So how are you going to do it?
I'm going to find out next time on Dragon Ball Z.
I'll give you a hint immediately here. Do I have to look at every single possible permutation? In fact, do I have to look at any permutation that involves DC, whatever, whatever, or CD, whatever, whatever, before and after it? Why? Because that edge is not present, right? By blindly generating every single possible permutation or combination for another problem that we're going to look at, you are doing more work than you need to. If I could cut out every single possible permutation with CD and DC, by the way, how many are there? You only have 4 things left to arrange, but you have this pair, this DC to arrange as well, because it could go over here, it could go over there, it could go anywhere. So you actually have 5 things to arrange. 5 factorial is 120. Double that up for the CD, and you've already cut out 240 possibilities out of the 720 possibles, right? So you've already cut your work in not in half, but in 2/3 of what it was originally, by simply just looking at the problem and taking the structure of the input into account. We'll talk about that. It's called backtracking, but more generally. But we'll talk about that next time, and hopefully OBS will be more patient next time. All right. I'll see you then.